Well, to begin with, water is going to evaporate from the sock into the bag's atmosphere. So we can represent that with an equation. Liquid water goes to form gaseous water. But eventually, the air inside the bag is going to become saturated, at which point water is going to condense from the air back onto the sock. So we have a second equation, H2O gas, going to form H2O liquid. Now, after a certain amount of time, remember this bag is sealed, we're going to establish an equilibrium. And in our equilibrium, we're going to find that water is going to evaporate and condense at exactly the same rate because it can't go anywhere. And we represent a system or a reaction at equilibrium with this double-headed arrow. So the sock is never getting any wetter, and nor is it getting any drier. This is a key thing about a dynamic equilibrium. The rate of the forward reaction, evaporation, is the same as the rate of the back reaction, condensation. But the reactions continue to happen on a molecular level. We can't see these little water molecules evaporating and condensing, but they continue to do so. Hence, it's an equilibrium and it's dynamic, it's continually moving. We can illustrate this graphically. On my y-axis, I've got amount of water, on my x-axis, time. Let's take our liquid water. To begin with, my sock is very, very wet, but as time progresses, some of that water is going to evaporate, and the amount of liquid water is going to decrease until it stops changing. Similarly, gaseous water, to begin with, we can assume that our atmosphere is completely dry. I've got no gaseous water to begin with, but as some of the water evaporates off the sock, the amount of water in the gaseous state is going to increase. Now, as we've said, at some point in time, the actual amounts of liquid water and gaseous water are no longer going to change because we're at equilibrium. The rate of the forward reaction is equal to the rate of the back reaction. So we can say at this point in time, equilibrium has been established. Now, it's important to note that once equilibrium has been established inside our plastic bag, the amounts of liquid and gaseous water don't change, but they're not necessarily the same. And we can see that where I've marked it on the y-axis here. The actual amounts are going to depend on a number of things, the conditions in our system. They're going to depend on how wet the sock was to begin with, the temperature, the pressure inside our plastic bag. And we can use the term position of equilibrium to describe this particular set of concentrations of reactants or products, in this case not so much concentration but amounts of liquid and gaseous water in our system. So let's explore this idea of position of equilibrium a little more closely. I've placed my bag in a greenhouse on a hot sunny day, and as the temperature rises, we would expect the rate of evaporation to increase because at higher temperatures, the air can hold more gaseous or vaporized water. But after a certain amount of time, remembering that this is a closed system, we will establish a new equilibrium where the rate of both the forward and the back reaction become constant once again. Except that now our position of equilibrium has changed. It's shifted to the right because at equilibrium, because we have a higher temperature, I have got a greater amount of gaseous water than I had previously. So my position of equilibrium has shifted to the right. So how might this change our graph? Well, at higher temperatures, we would expect the rate of evaporation to be faster. So water would evaporate more quickly and equilibrium position would be established more quickly. H2O liquid. Similarly, the amount of gaseous water would climb more quickly, and at equilibrium we would expect there to be a higher concentration of gaseous water than there was previously compared to the amount of liquid water in our system. And we can also see that, as we suggested, that at a higher temperature, with the rates of the reactions being speeded up, that we establish our position of equilibrium more quickly. Conversely, if I put my bag in the fridge, less water will evaporate, and it will evaporate much more slowly. So a new position of equilibrium would be established in which I have much lower amounts of gaseous water in the atmosphere in my bag and much higher amounts of liquid water. So that's the gas and there is the liquid. So once again, we've established a new position of equilibrium because the conditions in my system have changed, the temperature is lower. And what we can say is that the position of equilibrium has shifted to the left in response to me changing the conditions inside the bag. So to summarise, a dynamic equilibrium is established when we have a closed system, so one in which neither our reactants nor the products of our reaction can escape, and the rate of the forward reaction is equal to the rate of the backward reaction. Once we've established a position of equilibrium, the amounts or concentrations of our reactants or products remain constant. They don't change, but they're not necessarily the same. We can change the position of equilibrium, i.e. the concentrations of reactants and products at equilibrium, position of equilibrium, by changing the conditions in our system, by which we mean the temperature, the pressure, or the concentrations of our reactants and products. In our example, that might be analogous to how wet the sock was to begin with. In the next video, I'm going to go on to explore how we can manipulate the position of equilibrium using Le Chatelier's principle. And we're going to start to apply these ideas to chemical reactions rather than just physical changes. If this has been useful, hit the subscribe button, the effortless way to support your studies. And by clicking the link in the blurb below, it will take you straight to the Crunch Chemistry School, where you'll find all the resources you need to get that A-star grade at A-level. Together we can do this.